Hi everyone, Chris Tisdell here again. Thanks for tuning in. In this presentation, I'm going to continue my series of videos on matrices. Now, in previous videos, we talked about row operations and linking matrices with linear systems. We talked about row echelon form. In this presentation, I'm going to discuss an example that brings it all together. So we're going to talk about a linear system of simultaneous equations. And I'm going to show you how we can use row reduction and Gaussian elimination to solve that system. So let me share my screen with you and we can get down to business. Okay, determine the general solution to the following linear system by applying Gaussian elimination on the augmented matrix and performing back substitution. So here the unknowns are x1, x2, x3, x4. We've got three equations. So in the augmented matrix form, we take the coefficients of the unknowns and write them as columns in a vector. Columns as a matrix. Okay, so x1 would be 1, 2, 1, x2, 3, 4, -1, x3, -2, -5, -4, and x4, 4, 9, 6. Okay, we draw this in sort of in lieu of an equal sign, and then the right-hand side is our b vector, 2, 0, -6. Okay, so what we like to do now here is reduce this to something simple. Okay, row reduction and Gaussian elimination produces a form called a row echelon form, and it's a really nice form because we can decide whether our system's solvable, and if it is solvable, what the solution looks like. So let's work on this. All right, so the first part of the algorithm for getting this into a row echelon form is to choose a pivot entry. Now, luckily for us, there is one entry and it's in the top left-hand corner. So that is good. We don't have to do anything. If it's not one or it's not in the top left-hand corner, you can make it one or move it up to the top left-hand corner. Now, the next part of the procedure is to look underneath that pivot entry and make everything underneath it equal to 0. So I can do that just by adding rows or taking away rows. So row 2 would be row 2 minus 2 times row 1. Row 3 would be row 3 minus row 1. So let's write those down. So row 2 equals row 2 minus 2 row 1. Row 3 equals row 3 minus row 1. And you just add the corresponding entries together, okay? So 2 minus 2 times 1, that's 0. 4 minus 6, -2. -5 minus 2 times -2, so that's -5 plus 4, that's -1. 9 minus 8 is 1. 0 minus 4, -4. Okay, move on to the next one. 1 minus 1, -1 minus 3, -4 minus 2. Minus -2. 6 minus 8. It's -2. And -6 minus 4 is sorry, it's not 6 minus 8. I thought it was a bit wrong. It's row 3 minus row 1. 6 minus 4 is 2. -6 minus 2 is -8. Oof. Okay. Okay, so that's a good example of how just the little calculations can sometimes slip you up. I make lots of mistakes, so it's just better if we just go nice and slow. Okay, so that looks much better now. Okay, so now what we do is we move on to a sub matrix. So you cover that up and you go, okay, I'm going to put I'm going to row reduce the following matrix. And how do you do that? Well, you would normally make this -2 into a 1. But the thing is, the entry below it is a multiple of -2, so it's not necessary. Okay, so what I'm going to do is I'm going to keep that as my pivot. And I'm going to make everything underneath it 0 just by taking away 2 times row 2 from row 3. Okay, so row 1 isn't going to change. Row 2 isn't going to change. Okay, so -4 minus 2 times -2. -2 minus 2 times -1. 2 minus 2 times 1. -8 minus 2 times -2. So we get a row of zeros down the bottom. That's a good place for the row of zeros to be. Okay, so we now have our augmented matrix in a row echelon form. All the rows of zeros, if there are any, are at the bottom. Every leading entry of a row is, as we go down the matrix, is further to the right than the ones above it. So what do we do now? Well, you can see row 1's leading, okay, because it contains, it's non-zero and sorry, not row. Column 1's leading, column 2's leading, column 3 and 4 are not leading because column 1 contains the first entry of row 1, column 2 contains the first entry of row 2, column 3 and column 4 do not contain any of the first entries for any of the rows, okay? All right, so we can use that to our advantage, okay? We see, because this is a row echelon form, so see that column 3 and column 4 are non-leading, all right? So the variable associated with column 3 is x3. The variable associated, or the unknown associated with column 4 is x4. So what we can do is we're going to introduce parameters. I'm going to let x3 equal, lambda equals x3, and mu equals, say, x4. And this is a common theme that you can do if you have non-leading rows over this side of the matrix. What I'm going to do is then use back substitution, as they suggest, to get x2 and x1 in terms of lambda and mu. Okay? All right. So, all right, so we're working with this matrix here. Now, what do we see? Well, I see that row 2 gives us, it says -2 x2 minus x3 plus x4 equals -4. Okay. Oops, minus. Now I already have that these parameters for x3 and x4, so I can rearrange that. So bring those to the other side, and you can get x2 in terms of mu, lambda and mu. Okay, so if I take that over there, and then divide by 2, I'll get the following. Okay. Yep, so that's my expression for x2. And then I can use the row 1, that's x1 plus 3x2 minus 2x3 plus 4x4 equals 2. I can use that together with this and this to get x1 in terms of lambda and mu. All right, so x1 plus 3x2 minus 2x3 plus 4x4 equals 2. So make x1 the subject and just rearrange everything. And replace so replace x3 with lambda, replace x4 with mu, replace x2 with this, and make x1 the subject. Okay, so I'm going to get 2 minus 3 times x2, which is up here. Yep. Plus 2x3, which is 2 times lambda. Minus 4x4, which is minus 4 mu. So it's just a matter of simplifying this expression now. So I'm going to get you know what? I haven't divided that 2 out, so that should be a 2 there. Yeah, that should be a 2 for x2. And so that's a 2. So that's a 2. Okay, sorry about that. I forgot to divide that out. And let me just go over that a bit heavier. That's a 2. And therefore I'm going to get 2 minus 6, which is negative 4, plus 3 on 2 lambda, plus 2 lambda. That's 7 on 2 lambda. Minus 3 on 2 lambda, minus 4 lambda. So that's negative 11 on 2, mu. Okay. All right, so what have we got? We've got x3 there, x4 there, x2 there after I did the correction, and x1 there. Okay. So if I wanted to write this all as a parametric vector form, I can combine everything, right? I can write, you can write it like this. So write x1, x2, x3 down to x4 as a vector. So basically we've got negative 4 and 2 and 0 and 0 for the other parts. And then you can look at the common factor of lambda. So for x1, there'll be a 7 on 2. For x2, there'll be a negative 1/2. For x3, there'll be a 1, and for x4, there'll be 0. And then for the mu, x1 is there. x2 is there, 1/2. x3, well, x3 is just lambda, so there's no mu's there, so that'll be 0. And x4 is mu, so that'll be a 1. Okay. All right, so that's written then, I guess, in a vector parametric form. Okay, so the intersection will be a plane. Okay, bit of a long question, but what did you think? The principles for these kind of problems are very similar. You set up some matrix equation. You perform some row operations on it to reduce it to a row echelon form. Then you decide, okay, have I got a unique solution, no solution, or more than one solution? If you have more than one solution or one solution, you can use back substitution to solve that sort of consistent form. Anyway, hope you enjoyed this video. Thanks for watching. See you soon. Bye.